this point, we have looked at Newton's second law in one dimension, and we can solve for mass and acceleration and all sorts of fun stuff looking at F equals ma in one dimension. Now let's take it to two dimensions, and maybe even throw in some 3D. So here, let's say we're looking down on a mass from above, and it's on a frictionless surface, and it's subject to two forces. So it's moving in the xy plane. And let's give some numbers to these forces. Let's say that this guy here is 4 newtons going to the right, and this guy going up and to the right. We'll give it something fun to make the math easy. How about 3 root 2 newtons? And we will say that this angle right here is a 45-degree angle. All right, so now we know from Newton's second law that the sum of the forces acting is equal to the mass of this object times his acceleration. So can we use these to give the acceleration of the object? Let's add in one more piece of information here. Let's say that the mass is 2 kilograms. So we need to add up these forces because this sum is a vector sum, all right? And it's easiest to do that if we've got the two forces in component form. So let's call this one F1 and this one F2. And the component form of F1 is equal to, this is a 45, 45, 90 triangle, so both legs, because the hypotenuse is 3 root 2, both legs are going to be 3. So we've got positive 3I hat plus 3J hat for our component form, and this is in newtons. And for F2, our component form is even easier. We have only an x component going 4 units in the positive x direction, so positive 4I hat plus 0J hat, and that also is in newtons. So then the vector sum of these two forces is going to be the sum of their components. So we have 3 plus 4, 7I hat, and we have 3 plus 0, 3J hat. That is the vector sum of those. So now plugging that into Newton's second law, we know what the force is. It's 7I hat plus 3J hat. And that's equal to the object's mass, which I told you was 2, times the object's acceleration. Dividing both sides by 2 here, we get 7 halves I hat plus 3 halves J hat. And that is an acceleration. The units are meters per second squared. And that would be the component form of this object's acceleration. And now based on that, oh, remember, we've got an acceleration in 2 dimensions. It's a constant acceleration in 2 dimensions. So the x component of the acceleration is 7 halves. The y component of the acceleration is positive 3 halves. So we get to use everything that we learned about accelerations, velocities, and positions from the previous chapter. So if I wanted to, on the next page, we could go ahead and say that the acceleration at any time t was equal to 7 halves in the I direction plus 3 halves in, was it 3 halves? Let's go back and look. Oh, it was 3 halves in the j direction, and that's going to be in meters per second squared. And that'll give us the acceleration at any time t, the x and the y. If I want to find the velocity at any time t, the velocity is equal to the integral of the acceleration with respect to time. So we would integrate this, and we would have to need some initial conditions here. Let's just say that the velocity at time 0 is equal to, well, what am I doing here? Velocity at time 0 is equal to 0 I hat plus 0 J hat. So it starts at rest. That's our initial condition. So integrating our acceleration function, we have 7 halves t I hat plus 3 halves t j hat. And we could go ahead and integrate again, and sorry, this is in meters per second. We could integrate again to get our position function at any time t. And that would be 7/4 t squared I hat plus 3/4 t squared j hat, and the unit here is going to be in meters, assuming that my initial condition is r at time 0 is equal to 0I plus 0j. All right, so take a look at where we started. We started with these two forces that are going to make this thing accelerate at some direction in the xy plane, we found our acceleration equation using Newton's second law. Once we have our acceleration equation, we're in the same place we were back in the last chapter. We can derive the equations of motion for these. Notice the acceleration is constant because the force was constant. These two forces are constant. We add them together and we get this nice little vector sum here of this force plus this force. So this is the direction of the net force. It's also the direction of the acceleration. Divide this by the mass and you get the acceleration. Same direction, different magnitude. The magnitude of the net force was this, 7i plus 3j. The magnitude of the acceleration was this, the force divided by the mass, 7/2 I plus 3/2 j. All right? Notice I can get magnitude and direction from this. The acceleration is positive 7/2 in the I direction, positive 3/2 in the j direction, and we can get a magnitude and a direction of that acceleration by doing Pythag and inverse tangent for the angle. Go back to your force. If we wanted to get a magnitude and direction of the net force, again, draw in your components, 7 in the I, 3 in the j, and you've got Pythag to give the magnitude, inverse tangent to give the direction. All right? Let's take a look at another example where we derive the force equation based on other information. So now here's our example. We have a velocity function for the motion of a particle at any time t, 6t squared plus 4 in the I direction and 8t in the j direction. And I want to find the force equation at any time t. I need one more piece of information. Let's again say that the mass of this particle is 2 kilograms. So I go back to Newton's second law. I know that the sum of the forces, and I should write the sum of the forces. So this is a net force at any time t. The sum of the forces is equal to the mass times the acceleration. So I need to find the acceleration. I already have the mass, and that's going to give me the force at any time t. So if I get the acceleration function, then I can find the force function, the net force function. So how do we find acceleration from velocity? We take the derivative. Acceleration at any time t is equal to dv dt, the derivative of velocity with respect to time. So taking the derivative of my velocity function, I have 12t plus 0 in the I direction, and I have 8 in the j direction. And this is acceleration, so our unit is meters per second squared. So here's my acceleration function at any time t. My acceleration is this. Notice it is not a constant acceleration. The acceleration depends on time. So I can plug that in still to my force equation, my Newton's second law. So the net force at any time t is going to equal the mass times the acceleration function, 12t, and that's in the I direction, plus 8 in the j direction. And all I got to do is multiply each component by a scalar, which is the mass, which is really 2 kilograms. So then my force equation becomes the net force at any time t is equal to 24t in the I direction plus 16t, 16, nope, not t, just 16 in the j direction. And the unit here is newtons. All right, so we think about what that means. At 1 second, we plug t equals 1. We have a force of 24i plus 16j. At t equals 2, we plug in 2 for t. We have a force of 48i plus 16j. So we can find the magnitude and direction of the force at any time t. Let's do it. What is the magnitude and direction of the net force? I cannot write today. At 3 seconds. So we've got our force function. The net force at any time t is equal to, oh, I can't remember it. Got to go back. What was it? It was 24ti. 24t I hat plus 16 j hat in newtons. We plug in 3. The net force at time 3 is equal to 24 times 3 is, I don't know. I got to look on my calculator. Whew, okay, brain fart there. It was 72 I hat plus 16 j hat, and that's in newtons. So finding the magnitude here, we're going, woo, 72 in the I direction and only 16 in the positive j direction. So magnitude is going to be Pythag, and direction is going to be inverse tangent of that angle. All right? So now we just add in one slight complication to what we already knew. The sum of the forces is equal to the mass times the acceleration. So if we have the acceleration function, we multiply it by mass to get the force function. Sometimes we're going to have to derive the acceleration function by taking the derivative. All right? If we have the force function, then we can find the acceleration by dividing force by mass. Divide the force function by the mass, and you're going to get the acceleration function. If you've got the acceleration function, you can integrate to get the velocity, integrate again to get the position. All right? So adding one little wrinkle to what we've already done. So now we should be able to find the net force at any time t. We should be able to find the force equation given appropriate initial conditions. Good luck.